G'day, I'm Neil and my handle is Wiley11. I'm just going to put my disclaimer here. Whatever I do and say on these videos is well-intentioned and well-meaning advice. I accept no liabilities whatsoever for any disclosures. If you take some advice or act on something that I'm saying on these videos, you do so entirely at your own risk. I'm doing it based on my experience. These videos are my attempt to give back to YouTube for the help and assistance that YouTube has given me. So once again, you follow along or follow advice from these videos entirely at your own risk. Okay, and if you're not happy to do that, click this off and off you go. Because this is purely my attempt to give back to YouTube, as I said, for the help and advice that I have received out of YouTube. So this is just my little attempt to give back. If you're happy to follow along at your own risk, buckle up, sit in. Let's get into it. Hi, welcome to part 3 of our video on the PWM. So today we've discussed what a PWM is in part 1, and if you're coming in and you already know what a PWM is and you know how to build a flowchart, that's basically what we've done in parts 1 and 2. So if you want to go back and get some background and work out how to get to here, please go back, watch parts 1 and 2. Part 3, we're actually going to start working on our module, our include file. And what we want to do is we want to build on the work that we've already done. And look, and do this as a proper process. We've got our plan, we've got our flowchart. So from that, what we're going to do is identify what we call the methods. And within our module, there will be some variables called properties. And around those variables, we're going to build some methods for the computer to do, or for the processor to do, or for whatever it is we're trying to do. Okay. Sometimes we even know what we're doing. It's pretty overcast out there. There's a cyclone off the coast somewhere. Lord Howe Island's about to cop it sweet out there. So, hunker down, you guys, and be safe. But it's dumping a lot of rain on us at the moment, which is great because we need it. It's flooding all over the place at the moment, and we're in southeast Queensland in Australia, so we're getting quite a bit of rain. Now that said, as I said, we need it, and there's a lot of people out there that are really thankful for this weather, and at the moment it's cooling things down, and it's just really pleasant. It's even though it's overcast, it's pleasant. It's something that we're all thankful for. So thanks. Right, let's get on with it. So just give me a sec. Right, so part 1, we talked about. We actually didn't label what the sine waves are. They're an analog form of PWM, right? So sine waves are actually analog. But this is digital. It's a square wave. This is also digital. This can be digital, right? And that's what we were discussing. But what we've done here is we've discussed the digital one, and we talked about the duty cycle, right? And we talked about the components of the duty cycle, the PWM, or the properties of it. And we said it had a magnitude, we said it had a duty cycle, and it had a frequency. Now, I just want to quickly do something here. I'm going to do it just on a bit of paper, because there's a relationship between the frequency and the duty cycle, and we're going to discuss that right now. And I might swap cameras. Just give me a sec. Okay, so we're recording. I'm not sure that we meant to, but we are. I just want to make sure that strap's there in case that camera falls out of that holder. So we talked about frequency being cycles per second, and we talked about duty cycles active being seconds. So if we know frequency, right, if we know frequency and we've got cycles per second and we've got duty cycle being a percentage of the cycle, we have what we want to know is how many cycles there are in a second from the frequency. So let's take the easiest frequency, right, which is 1 Hertz. So we have cycles per second, right, and we know how much time there is in a second. So what we want to do equals, we want to know what the cycles are, equals 1. So we got 1 Hertz, right? So we have 1 cycle per 1 second equals 1 duty cycle. Right, and what we want to know is if we set 1 second, we want to know how many cycles there are. So if we have 50 Hertz, then that changes to X equals Y duty cycles. So if X equals 1, then Y equals 1. If X equals 50, then Y equals 50. You see what I'm saying? That's our formula. X cycles per second over Y cycles equals how many, right? So now we've got to know is how many ticks of our computer make up 1 second, and the answer is 1 million. Right, so we've got 1 million is 1 megahertz equals 1 megahertz. So now we've got to equate this 1 million megahertz to this 50. So the way you do that is you cross divide it. So it's 1 million over 50 gives you how many CPU ticks you need to make up 50. Does that make sense? So the answer to that is what? You take that off there, so that shifts to there, divide that by 5, and the answer is 20,000. So 20,000 beats of the CPU equals 1 cycle. Does everyone understand that? That's 1 million on this side and 50 on that side. So 1 million over 50 is 20,000. Hopefully I've got that right. No, it's not. I've lost a 0 somewhere, haven't I? No. Multiply that by 50. No, I was spot on. It's 20,000. So 20,000 times 50 times 50 equals 1 million. Now if the speed of our processor is 8, then you've got to divide this number by 8. Sorry, multiply this number by, if you multiply that by 8, you multiply that by 8. So our 20,000 becomes 160,000. So if you've got an 8 megahertz processor, that's 1 megahertz.
at 50 hertz. So to get 50 hertz, we need 20,000 ticks of our processor. This is important stuff when we come to write the program, right? We've got to know these numbers. And it's a little bit of maths, but it's pretty simple maths, and I'm going to do it again on the computer so that it makes a bit more sense. But I just wanted to swap over and do out this cycles per second so that you understand that the relationship between cycle and duty cycle is 1 to 1. So if you want 50 per second, then you need 50. If you need 200, then you need 200, you know. So coming up with the 50 is this little equation here. And then we swapped over. Hopefully you can see this. It's right at the edge of the screen. Yeah, everything's going to go to crap now. This 1 megahertz, right? So 1 megahertz is 1 million ticks of a CPU. And to get 50, you just divide the million by 50 to give you 20,000. So if we wanted 50 hertz, we'd get 20,000 here. So you can see that a million over 50 would equal you 20,000 if you cross divide it. Get that 50 over here, you've got to divide it. So if it's an 8 megahertz, then it's the speed of the CPU over cycles. So what we're saying, it's speed of CPU, and that's usually megahertz, right, over frequency, which is in hertz, equals CPU ticks. Because these are hertz, so what we've got is two frequencies. And we need that number. So if this is 1 megahertz, and that's 50 hertz, then this will be 20,000. Okay, so that's your equation right there. So if this is 8 megahertz and that's 50, and that's 160,000. You just multiply that by 8. So if you've got an 8 megahertz processor, then you need 160,000 ticks for that to happen. Alright, so that's the basis upon which we write our code. So let's get back to it.
Hey, and welcome back. Alright, well, I've got a brush car working out there. I've got a TV going across the way from the bloke across the way, so if there's a bit of background noise, do apologise. But we wanted to get back into this PWM routine. Now I started to do a bit of research because what we're doing is we're coming up with one of these things, a pick. We're using a pick at 3. Now this is a clone one. Unfortunately I got ripped off on eBay. I thought it was a real one, but it was a clone one. So I paid way too much for a fake one. But it works, so that's what I'm using. So what's going on? I've got my knickers in a knot. I started to sort of put together an algorithm to build an include file. Now in assembler, you can use these include files as a kind of a header file. The problem with these things is that while you can recycle them, you can't do that until you've tested the actual methods, and they're actually harder to integrate than just writing a straight script, is what I'm telling you. And I disappeared down a bit of a rabbit hole doing the research. So it's been a couple of days since you last saw me. I've been trying to do a bit of research so that I know what I'm talking about when I come in here and start telling you guys what I'm trying to achieve. And I've kind of wasted 4 days. When I say kind of, I have wasted 4 days because I've changed direction. So we're going to take this. Well, this one will do us. We're going to generate this square wave, right? And that's going to be our goal. And we're going to do it building on the way we did the series on the PIC 12F675 blink like an Arduino. Now, if you haven't seen that series, it actually does things the right way, and I've got the code for that. But the thing I haven't done with that is I haven't really done the duty cycle and the Watchdog Timer bit correctly. And I want to come back to it and fix it so that we can equate the Watchdog Timer settings to hertz. Now, it's a bit tricky because in the PIC 12F675, the Watchdog Timer is its own little animal. It doesn't rely on the processor's internal clock at all. It's got its own little separate thing going on. And it's all internal to the chip. So it's nothing that you can look at or check or measure or anything like that other than to program it and, you know, look at it with an oscilloscope. But that said, there's a way to equate the values, the valid values for the prescaler in the Watchdog with the frequency. So what we need to do is to work that out. So all this work we did on CPU ticks versus CPU cycles versus frequency, right? That's all going to get put to one side for a minute. When you program a timer, different chips have different things, different ways, different values. And what I wanted to do was set up a little table of values that says it has 3 options, right? So basically you have your first option, which takes up the bulk of the time in the duty cycle. Then you have the second option, which takes up, what am I looking for? It takes up the bulk of the rest of the time, and then you have a third option, which is the fine tune. So you have 3 columns, and what you're doing is you're setting that Watchdog Timer prescaler based on those 3 values. So in value 1, you've got the bulk of it. In value 2, you're going to get really close, and then in value 3, you can fine tune it down to 1% of your, you know, plus or minus 1% of your required frequency. I think that's the way I want to go. I think I want to build this matrix up based on the information in the data sheet. I'm going to go away and do that research, and I'm going to come back with a built matrix. I will show you the source document and where I got my information so that I could put together a little spreadsheet, which I'm going to do. I'm going to work out my values so that I can generate my matrix, my table of values, and I'm going to limit it from 20 hertz right up to 50 hertz, right? If you want to go higher than that, you can continue. you can build the table, but you're eventually going to start using up a fair bit of memory, and you need to write this value, this table, into ROM when you start. So you're using up a chunk of your ROM, and if you're not going to use all, but you're only going to look up one value. So for 30 hertz, it's going to go into the table. It's going to go, oh, you beauty, and return a single value of three numbers, a matrix of three numbers. I think that that's a brilliant way to do things. We may go out of assembler. We might abandon using assembler. I might decide to go over and use a C, the C system, and use a C program, and use the C compiler in the systems. Now, I don't like that as much as assembler. The reason is that you have less control over what you get back from the compiler, and there could be all sorts of garbage in your chip that you didn't want there. I like assembler because what you see is what you get. So with the microchip system, you ask for that and you get that back. With the C system, you're going to your computer's compiler and compiling it. Whatever's in your computer is what you're going to get back. And if you've got all sorts of bits and pieces around the computer, you don't know what libraries are being employed or deployed or unemployed or whatever. Well, you don't always know. You might think you do, but you don't. So, if all I want my chip to do is to blink on and off, then I don't particularly want it sending messages to Russia. I'm not saying it would do that, but who knows? Who knows? All right, what to do next? I think I'm just going to stay focused on doing the research. I might swap this whole exercise into C and do it as a C project where we generate this. There's any number of things we can do here. Like we could swap it into code blocks or something like that. The whole project out of the microchip assembler and put it into code blocks and work out how to use this with code blocks. I think that'd make a cool project, because I'm actually unsure how to do it with code blocks and that. Or I've never actually done it with code blocks. I've always used the microchip software, and I've always done it with assembler. But at the end of the day, you've got to operate where you're comfortable and where you can get the results. And the options are we can stay in assembler and just write a single script that does what we want. And then we might have a lookup table where you manually set the values for the watchdog. So you run your finger down the ready reckoner and you go there and you put them in your script, and they're what you get back, right? So for 50 hertz, this is what you need. Bang, bang, bang. And you get 50 hertz back when you put them in your script. Now, I think that and that could be WDT1, WDT2, and WDT3. I hate doing that. I really do. I hate doing that sort of stuff, but it will work. It'll get us a result. It just means you've got to create your ready reckoner table to get your result. All right, so let's get on with it. Let's try to make the chip do the work based on just the two input variables. The program, the computer, the chip can do the work. It's got enough commands in there, it can do it. It's just that you've got to figure out how to use those command sets to get what you want out of the chip. And as I said to you, we're going to find out that I disappeared down a rabbit hole for 4 days, and I've come back and I'm as confused as I was 4 days ago. I don't really have a plan other than we've got this flowchart that's start and finish, and that's where I want to go. But I don't really have any clear direction yet as to how I'm going to get there. So I'm going to chop this part off. I'm going to call this part the end of part 3. And we're just going to go on with part 4, which is going to be planning, well, I'm going to chop this off here for today, and I'll continue when I've got some kind of solid plan for moving forward. So we're gonna pick it up some point in the future, but you'll see the next part of this video when I've got some kind of a working plan. Righto, so I'll sign off for now, and I'll see you when I get back to this. Hey, welcome back. Been a few days since I've been on YouTube. I'm looking across at some stuff here that I've got on my left, and I'm looking across at some stuff that I've got on my right. Because on my left I've got a chip, and on my right I've got a bunch of notes. I've literally gone down a number of rabbit holes. I still am seriously confused about how to get to a result that I want. The reason is that I've been on YouTube and on forums and things, and I've gone down so many rabbit holes that I've almost given up. It's so hard to find what you want exactly. And if you ask someone a question on a forum, you get back all these well-meaning responses which are nothing to do with your question, and then they start arguing with each other about, no, that's not what the guy wants. No, I know it's not what I want. What I want to do is delete all the argument and just get to an answer. But they argue, and the comments go and they go and they go. Yeah, and there's thousands of them, and you're like, what the heck? All I want is an answer. All right, so that said, this YouTube is starting to look a bit like one of those forum things where I've said to you I'm going to do this stuff, and suddenly I'm not doing this stuff, and I might have to rethink what I'm trying to achieve with this thing. So everything's about the journey. I just want to make that clear. Everything I've done, I've learned something, whether it's been, just how to make a better declare, how to work out what kind of variable you can get away with, like saving space. I don't know what the story is with these people. They're passionate and adamant that they're right, but they're all arguing with each other. And I'm like, well, I didn't want any of the argument. I just want an answer, or a suggestion, Now, many of the suggestions are completely off base. They're just not even close to the question that I asked. It's like, how do you paint a car? And then they start arguing about which colour you should paint it, That's what I'm saying. You don't want to do that in the forums. You just want to give the answer you have, or the suggestion, and then get out of it. Just here's a suggestion, see you later. Now, if someone else has got another suggestion, they're more than entitled to put it in there. But all you want is the suggestion. If you go, right, and then what you do is you reply, say, right, this is what I used, and it's exactly what I wanted. Thank you very much, and then close down the issue. That's the way it should work, but it doesn't. It just doesn't. So I've been a few days, again, probably, let me think. It's been 4 days since my last video update in this clip, and I'm still no closer to getting to where I want to go. So I'm just going to swap cameras, and I'm going to talk about the flowchart, and I'm going to talk about what I've got. This window here. I've got a brush cutter going over there, I've got a mower going over there, and some guy with a grinder going off at the construction site just over there. So apologies for the background noise. I can't close the window because I'll lose my breeze and cook. I need the breeze. Alright, so let's talk about where we're at with this. I've thrown this together based on our flowchart, and what I've done is I've done my commenting at the top of my form with the original date that I started in version 1. This might change this date because I want to make sure that I say this is going to be version 1 and it's going to stay. This is not going to be our final version. Let's make that very clear. This is just going to get a result, and I've followed our flowchart. Right, I've said collect the properties data. Right, here we go. Collect the start, set up the chip with known inputs and outputs. So I've actually had to put sort of the start in here. Right, now all the stuff that I've done here I can achieve. So I just want to talk a little bit about the setup, and down here I've got this call out that says set GPIO out. Right, now up here I've declared it and I've given it a default value of pin 0, and I've said that I want it to go out to pin 0. Right, so in this instance this call out is superfluous. Alright, so this is not efficient code. We already know it's not going to be efficient. I know that, right? I'm just not going to bother with that. I'm just going to, after I get this variable, I'm going to set this. And then I've set up some system registers to store some values. And I've just said I want a current value, an active value, and a passive value. And I've just nominated 3 registers. These are user registers that you can get these out of the data sheet. So all of this information here, from there to there, has come out of the data sheet for the PIC, the 12F675 data sheet. So now this is standard stuff, right? I always start my program, blah, 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 call, BSF, and set up. You can see here I'm setting the pins into the what they call the tri-state input outputs, right? Move it in and setting up the weak pull-up register because I want the inputs to be high, right? So I'm just enabling that. So if they want to go high, they must go high. I don't want them going low for any reason. Clear the interrupt controller. Interrupt output controller disables it. And set myself back to register 0. Right, so that we can operate in the standard bank of registers in the CPU. Then what I'm doing is I'm clearing the registers and then I'm calling the calc cycles. So these are 2 routines that don't appear here. Well, in fact, clear registers does because it's here. Here's clear registers, and all I am doing is I'm clearing the GPIO out. I'm setting them all to 0. I am clearing all of my registers that I've instantiated. I'm not doing anything with them. If someone wants to overwrite them, they can, because I'll come back and reinitialize them at the top. Error message is in. So I've done this bit here. I haven't done this, verify, right? It's up here. And I've just put this will be done later. So I'll put some sanity checking in here. And if it doesn't work, it'll go here. And in finish up, all I'm doing is clearing the registers. I'm just dumping out and clearing the registers, and that's quite acceptable. So, and then you can see the program will end. It won't do anything else. We haven't built this area in here yet, but we've built kind of all of this stuff here, and we've got some idea of how we can build this. We're not worrying about the system interrupt. The system interrupt is coming in externally, but if it goes on interrupt, we need an on-interrupt method that takes us into this clearing our registers, right? So if we get interrupted, we want it to finish up and end. So we've got to deal with that, but I'm not going to deal with that in this process. I'm going to deal with that somewhere else. So we've got a plan of attack. We've got somewhere we can go and we can deliver this. We can actually deliver this working in version 1. And what we're going to do is we're going to break this out. And as I said to you in the introduction, you're going to find that these little simple flowchart thingies are often not simple. And we've already hit that not simple bit, because we are 8 days in and we're no closer to getting a solution to this. So what I've decided to do is to just write it. Just write it. Just get some kind of a pulse width happening, and then go in and make it what I want it to be in bits. How do you kill an elephant? Well, how do you need an elephant? Well, this is our elephant. One bite at a time. So one bite at a time says, let's just get it going. Then let's go back to it and make it what we want. Okay, one bit at a time. These are easy. These things here, they are easy. Set high, set low. It's actually set the output to the opposite of the output. You see that? Here it's high, here it's low, and then it goes around a circle. Here it's high. So this is just a toggle. So all this is doing is inverting the value at the pin. It's just saying set it up, set it down, set it high, set it low, set it high, set it low. We can just do that. We can ignore this. So we could do this, we could do this, and we could have it high, low, and we could ignore the fact that we need it to sleep. We could do that. No worries at all. Except that I want it to sleep in the middle, and I can do that. I know how to use the Watchdog Timer to do this. So we're just going to set it high, set the thing to sleep, set it low, set the thing to sleep. I know how to calculate the cycles. I can just do it as a lookup register, but for the moment, I can just hard code the values into my calc cycles. So down here in calc cycles, I'm going to say needs revision, hard code values, or hard coded values return. So I'm just going to put my values in there, right? I'm just going to say I want a 70%, I set it up here, frequency. I wanted a 60-40 duty. I want it active 40% of the time. Oh, I keep getting this thing. Here I want 40% active duty cycle at 50 Hertz. All I'm going to do is I'm going to figure that out using a spreadsheet, and I'm going to key them into here. So I'm going to set up the values in my registers, right, that I need. I'm going to store them away, and then I'm going to use them in my main loop. So we're about to do that bit, this calc cycles, and then we're going to return. We're not going to do anything, and then we're going to drop down. See here, this is where we're going. We're going to do that, which will come down here and return back into the stack, and then it'll clear the stack here. It'll clear the stack, and it'll come into main, and it'll start our loop, our main loop. So it'll be taking off the top of the stack and running this loop. And this is an infinite loop. It just keeps going round and round and round and round and round, and doing this round the loop part of our, see this round and round and round and round you go. That's what we're doing. We're going round and round and round and round until we run out of things. Now here you can see our declares. So I want to come back up here for a sec. Frequency. Here's frequency. Active duty cycle percentage. Here it is. CPU speed. Well, we already know it. So we're not declaring that. We're not asking for it. We're just calculating it. and it's done here, calc vowels, calc cycles. That's what this is doing, call calc cycles. So CPU speed is now a method. PWM pin, here it is up here. So these three inputs we need from the user, 1, 2, 3, right at the top of the program, right? So we're going to do that, we're going to run the program. Now if I compile this, you'll see that it will succeed, he said with confidence, right? There are no errors, right? So my compiler is telling me we're all good. And we're doing it as a single assembler script. We are not doing the modular stuff that I want to do. So we've now got a plan. We've got a plan of attack that's going to get us to a result. And I prefer to get to a result and then work forward from a result. Once I get it blinking the way I want it to blink, then I'm going to clean it up. I'm going to come back into it and work out how do I do a lookup table with this calc cycles. So I probably want to get into my inc file here, which I'm pretty sure I've done before. Just going to open this one up. Here it is. Right. So you see, these are lookups. Here it is here. So all this is a complete lookup table. And what I can do, this is list 1, right? So this is a list of values. Here it is. A whole bunch of them. It's our GPIO, right? So we can either define, we can ask for GP0, GPIO0. We can actually nominate these. Here's our bank 1. Here's our bank 0. Here's our Trizio. These are bank 1, bank 2, W and F registers. Up here, they've told you what they did. They've done list at the top, no list. If not defined, that verify the selected processor. So there's their sanity checking. It's quite neat. And then they've gone ahead and done this. So if you've included this, you're going to get an error back. Here's the error message. So if you haven't declared the 12F675, then the header file mismatch, verify selected processor, end if. So if you haven't defined that, they're sending out a message. We could take this and generate it as a message, a warning. And we could do our sanity checking this way. So So down here where we've got verify, we can do it. We can just chuck it in there. We're just going to change this. This code only tested for PIC 12F675. Alright. So there's a nice simple sanity check that we can do in our verified data. Let's see if that compiles. There we go. We got an error message coming out. So we're doing this bit. Quite happy about that. And all we did was pull it off someone else's code. Works beautifully. Here it is. Build succeeded. Now where it'll come out, let's say that. Let's quickly make that. And let's see what happens. Warning, here it is. It's not our warning, it's someone else's. Processor superseded. We've got a 215 warning. I expected to see our warning in here somewhere. Alright, so maybe it's not that simple. Well, we'll play with that later. It's not impacting us, but we're getting a warning from the system if we change this out. I don't know. Let's comment these out. See if it'll build. Oh dear. There's a whole bunch of it. I don't know what the hell you're talking about. Alright. And it's telling us that our output file is out of date. Right, fine. Let's go back to our code. Let's stop playing before we break something. We definitely need our list and include. Let's save that. Let's compile it. We should get a successful build. We're just playing. We're just learning as we go. And this is what it's about. It's a bit of fun. Some of you are laughing at me because I'm struggling with this, but it's all about the struggle. Sometimes you have to move forwards at your own pace. I'm 8 days down a rabbit hole here, and I'm completely confused by all the advice I've got back and looked up and everything else. So there's no really right way to do this stuff other than what works for you, and that someone can follow along behind you and look at your notes and go, oh, well, I can see what he's trying to achieve here, right? And maybe they've got a better way of doing all this stuff, right? Maybe there's a better way of doing this, and I'm not going to say there's not, because I'm not the expert in this stuff. Obviously, this isn't doing anything at the moment, but let's just leave it there for the moment, because this is very important. What we should be able to do is something like this. Here, yeah. So if we put out the message, there it is, it comes out. Here's our message. And it builds. So there's our warning. Excuse me. It's there. Isn't it cool? So we know that the message bit works. I'm just going to control Z, 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 Z. Let's just go warning. I'm not sure what this is all about at the moment, but I'm going to have a little play. That should build without our warning. The message is gone and our build has succeeded. Okay. I'm going to pick this up probably tomorrow now. I've got stuff to do. I've got a meeting to go to. All this stuff that I'm doing here, like this is the journey. This is warts and all journey, and I'm going to keep going with it. Like we're 15 minutes of talking about this stuff, and what we've got is something that just compiles. We haven't even begun to do this, right? So we need this happening. So we need to build this out, and we've got to do a set watchdog timer. We've got to do, so here we've got to set the watchdog timer in this method. We've got to activate it by putting the system to sleep, make sure it wakes up at the correct moment, and then build the toggle bit. And toggling the value in the output is also an interesting one. You know, how do you toggle it? How do you toggle it from on to off? So, yeah, it's nice. Just going to save that, and I'm going to call it a day. And I'll catch up with you when I've got some time. Right, so you may have realised that we didn't get anywhere near writing a piece of software today. I'm completely lost. Being honest, this has been an epic fail, this particular part of the project. But I'm not hiding anything. I'm giving you warts and all what's going on, because this is all part of the process. This is all part of learning. And you can see I'm just feeling my way through this. I'm no expert when it comes to this stuff. I know enough to get myself into some serious strife sometimes, you know, but I can recognise when to stop, sit back from it and go, hey, you know, let's have another look at this.
And I've done that so many times in the last 8-9 days. I get onto something that's promising and I get into it, and I've got notes up to yin yang. I've got all this blasted. Here we go. I've got all these notes that I've written and websites that I've done, and you know, things to look at and calculations I did and this stuff and whatever else. And it's all basically going to get, well, I don't know that I'll shred it, but it's not going to get used in this project. It's going to get used elsewhere. Some things I've learned are good for other things. So I'm going to wrap this up, and I'll catch you in the next video.
So if you liked what you saw, please like the video, subscribe to the channel. Don't forget to support my company, nightglowmanufacturing.com, so that I can keep making these videos. I want you to make good decisions, do good things, and let's all get along. Let's make life a lot easier for everyone when we all get along. And I'll see you guys at the next video.